In this video, I'm going to implement printf on this microcontroller so that I can print formatted strings to a terminal. Or well, I'm not actually going to implement printf myself, but instead I'm going to include an external open source project into my project. And I'm going to have this printf implementation called the UART driver that I implemented in the last video. So you should view the last video as the part 1 and this video as part 2. And just to remind you, the reason I'm doing this is because when you're developing an embedded system, it's useful to have a way to send data or log traces from your, in this case, microcontroller or your embedded system in general, to your computer, the terminal of your computer, so that you have another view into what goes on inside your embedded system, which is especially useful during development. And normally, when you write a C or C++ program on a normal desktop computer, logging traces to the terminal is trivial, because the only thing you need to do is include a single header and then you can call printf as is, and the operating system is there to do the heavy lifting to make sure that your strings show up inside the terminal when you run your program. The same cannot be said for a microcontroller project, because on most microcontrollers there is not going to be an operating system there to do the heavy lifting, which is also the case in this video series, because on this project, I'm just writing all code bare metal, so there is no operating system there to help me out. And this means that it's up to me as a developer to decide what's going to happen when I call printf on this microcontroller. But normally, what you will want to happen is that the call to printf leads to some underlying call to a lower level driver that sends the individual characters of the strings over some communication interface that's connected to a host computer that can display the characters on a terminal. And as I said, in this case, that lower level driver is going to be a UART driver, the one that I wrote in the last video. And there are a couple of reasons why I'm going to use an external implementation of printf. First of all, it makes it really easy to decide what happens under the printf call, because the implementation I will be using is just going to have me implement an additional underlying function that's going to call the UART driver that I implemented in the last video. Secondly, the standard implementation of printf is usually really large. It takes up a lot of flash space because it handles all of these different formatting options. And I actually showed you in an earlier video how much space it actually takes up. And on this microcontroller, for example, I only have 16 kilobytes of read-only memory or flash memory. And this means that I need to be careful about how I write my code and what external dependencies that I include, as to not run out of space before I'm actually done with my application code. Thirdly, I could, of course, implement my own implementation of printf, but that would be a bit tedious, and I see no good reason to do it when there are so good external implementations and open source implementations available already. So I'm going with an external implementation to also save me some development time. And the printf implementation that I will be using in this project is the following. And I've already showed this project in an earlier video. So this is a printf implementation that is tiny, fast, and aimed at embedded systems. And it's also extensively tested. And it's easy to use. It basically just has two files, a header and a C file. And the only thing you need to do is to add an additional header file to add some configurations, because you can disable support for different formatting options. So for example, I will be disabling support for float and exponential and some other things. And other than that, the only thing it requires is for you to implement a function called _putchar. So this is the function that I will add to my project, and this function is going to call the UART driver that I added in the last video. And I've actually already included this project as a Git submodule in a previous video. So it's already available under the external folder, so external and printf, so it's available under here. And I've added it as a Git submodule like this. So to add the configuration options for this project, I just need to add a single file. And I'm going to add it under this folder, the external folder. and name it printf config.h. And this file is then included by the printf implementation. So in the C file, it's going to be included here. And to make this work, I'm also going to have to pass a compiler define, which I will add to the make file. So let's add the options inside this file first. And I'm going to disable these four. And the reason why I'm disabling these is because I'm not using them, and by disabling them the printf implementation is going to take up less space, so it's going to save flash usage. And all of these options are described in detail in the readme of this project. And then I can jump over to the make file to add the compiler switch. And I also need to make sure I add the implementation file from the external project, so it's built as part of my project. Then I can try to build this. Well, I shouldn't have source here. It should just be external. Like that. And then, as I said, this project requires this function to be defined. So now I'm going to add this function. And I will add it in the UART.c file. And it's basically just going to be this function, so I can just replace the name here. Like that. And here. And I will also remove this function now, since I will be using the printf function instead. Can also add a comment on top of this. In the last video I also forgot to use my define for an interrupt function, so I'm going to replace this here as well in this video, just to make it a bit more readable. So I have a define called interrupt function, so I can write it like this instead. So it's this define right here. And to use that I also need to include common/defines. And now, since I removed the function and renamed this function, I also need to fix my test file. So I'm just going to call Butcharia instead. And I can just build this test function again to make sure that it actually works. And also flash it to my board. So now if I flash this and then open my terminal, I should see artful printed. And I do, so it's still working. Then I can actually move on to make use of the printf function. So I'm going to create another test function in this file, and I'm going to call that test trace. And similar to here, I'm going to initialize some things. Then just 3, which is the year right now. also need to include the printf header. I think I need to rework my make file to be able to include it like this. Yeah, I'm going to remove that and have it like that instead. So now if I build this, that works. And then I can try to flash this as well. Okay, so now this test function makes use of the printf function from the project that I have included, the external printf implementation project. So now if I open my terminal, I expect to see artful bytes and 2023. Yeah, and that works. And now it prints really fast since I don't have any busy waiting in between. So I'm just going to add a busy wait here as well. Okay, so the big win with being able to call printf is that I can pass integers like this. So I can write a string and then I can include an integer number like this. So for example, if I have a variable, I can call printf and print the value of this variable, which can be very useful sometimes to understand what's going on inside the program. So I can write something like this then. And the printf implementation takes care of formatting this number to a string in a space efficient way. What I'm going to do now is to add a wrapper around the printf call to make it a bit nicer, which I alluded to in my software architecture diagram. So I'm going to add this module now, and it's just going to be a header and an implementation file pair. And I'm going to add them under common because I should be able to call the trace function from my drivers and my application files. And I'm going to make the trace call more useful by prefixing every trace with the file name and the line number. And I'm going to do that by using preprocessor directives. So this macro is going to take the same parameters as the printf call. And then I have to write it like this. And then I'm going to have a trace function that first prints the file name and the line number, and then the formatted string, followed by a new line. And to get the file name, I use the preprocessor __ file. And to get the line number, I use the preprocessor directive __ line. And then I can get the arguments by writing it like this. And then I'm going to have two functions here. One function to initialize the trace functionality. So this function is basically just going to call UART init. And then the trace function that I'm calling here, the function that's going to wrap the printf call. And then I'm going to add an additional define here so that I can easily enable and disable traces in my builds, because sometimes it can be useful by the end of the project to simply remove all of the traces to save space and also for debugging purposes, since all of the traces may affect the timing of the code. So if I pass disabled trace as a define, the trace init and trace function shouldn't do anything, so I'm just going to overwrite them with a macro define. Like that. And then I can jump over to the trace.c file and first of all include common/trace.h, and I'm also going to wrap this inside the disabled trace as well. And similar to all of the other init functions, I'm going to have an assert to make sure that I don't call this function multiple times accidentally. and a bunch of includes. And then as for the wrapping function, I have to write it like this. And I should never call this function unless I first have initialized. And it's actually a bit messy the way you have to wrap the printf function, since the second argument is a variable number of values. So I had to Google this to understand how to do it, and there is a Stack Overflow thread that explains how you do it. So I basically just copy the way they do it here. To be honest, I don't fully understand this, but I know that it works. And then I also have to add trace.c to my makefile so that it gets built as part of my project. And then I can modify the test function to make use of this function instead of calling printf directly. And since I already include the new line inside the macro define, I don't need to add it here. So I can write, yeah, and this should be all uppercase. Then I include it like this. And then if I build this now, I get an error, and that's probably because I haven't included everything I need to include. Yeah, I need to include external printf.h. Yeah, and then I can flash this. But it doesn't work, of course. So let me analyze why it doesn't work. Oh yeah, I should be calling trace init here instead. Now it works. So as you can see now, I not only print the string that I have here, but I also print at what line this trace is called. So it's called at, in this file, test.c at line 164. The downside with adding this prefix here, of course, is that it's going to take up additional flash space, and the flash space it takes up is going to depend on the file name. I could make this better by only including the file name and not the entire path, but then I have to mess around a bit in the makefile to just extract the file name, and I'm going to avoid that in this project because I don't want to make my makefile more complicated than it already is. I might do that optimization later on if I end up running out of flash space. But for now, I'm just going to leave it like this. Okay, so just to revise, what's happening now when I call trace is that this is going to call the trace function that I have in my trace.c file, which in turn is going to call the printf function that is implemented in the external project that I just included. And this printf function is going to do a bunch of things. It's going to translate the values that I pass into strings and merge it into a single string. And then finally, it's going to call the put char function multiple times, once for each character. And this put char character and this function is the one that I have implemented in my UART driver. So this is going to fill the UART TX buffer with a character to send over the UART line that's going to go through the UART to USB bridge and then to my desktop computer to show up on my terminal. So now I can commit this, but before I do, I need to modify my makefile to make sure that I don't run formatting or cppcheck on the files from the external project, because I want to leave those files unchanged. And I thought that this already worked for the cppcheck, but I haven't been able to make this ignore flag work, so I'm going to remove this and instead do it another way. So I'm going to add the files that I don't want to run through cppcheck and formatting to a separate variable. And so far this is just going to be the two files from the external printf implementation. And then I can use the make function filter out to filter out these files from the rest of the source files. There might be a more elegant way to do this, but I couldn't figure out a better way, so this is the way I do it. And then I can just make use of these variables inside my format and cppcheck rules at the bottom. So if I run cppcheck and format now, it shouldn't touch the files inside the external project, so it shouldn't touch these files. And then I can also go ahead and run the script that builds all of the tests to ensure that that also works. And before I commit, I should also create a new local branch. And I'm just going to call that feature trace. Then I can just quickly run git diff to see that the differences make sense. Okay, so now it seems that the formatting actually ran on the files inside the external project. Oh yeah, I need to change this as well. Now if I check out these changes. Okay, so now there are no changes inside the external project. And then if I run make format, there should still be no changes in that project. Yeah, so now it works. And then I can go ahead and add my changes and then commit them. And then I can push this new branch. And open a pull request. And check to make sure that it also passes CI. It failed. I made a mistake, I forgot to add the new files. So if I commit amend this and then push force to the same pull request. And then another thing I need to do to make this work is to make my GitHub action also clone the Git submodules. Which I can do by writing with submodules true. So now the CI passed, but I'm not actually going to merge this pull request just yet, because there is a second commit that I would like to make in this video, and that is to add a printf call or a trace call to my assert function, the assert function that I added in a previous video. Because right now what the assert does is that first of all it triggers a breakpoint if a debugger is attached, and then it just blinks the LED. And to make the assert even easier to find and spot, I also wanted to send a trace when the assert occurs, so that I can also spot it on the terminal when an assert occurs. And to minimize the amount of flash space used by the trace from the assert, I'm just going to have the trace inside the assert trace the value of the program counter, the register that holds the address to the current instruction, and then I will be able to use this program counter value to retrieve the file name and the line number using a command line tool called address to line. So let's jump over to the current assert implementation. So right now the assert implementation is defined as a macro that in turn wraps a function called assert handler. And inside this assert handler I first trigger a breakpoint, and then I configure the IO pins to be able to blink the LED. And here is where I'm going to add a call to trace the value of the current program counter. And similar to how I did it for the blink LED functionality here, I'm going to make this as isolated as possible, just to minimize the code dependencies inside the assert handler, so I don't accidentally end up calling functions inside the assert handler that in turn calls asserts themselves, leading to the assert being called recursively endlessly until a stack overflow happens. So to do that, I'm going to add a special UART function that I'm just going to use inside the assert handler. This is going to take a string. And then I'm going to use the sn printf function from the external printf implementation to create a string from an integer. So this function first takes the pointer to the string I'm writing to, and then the second argument is the maximum number of characters to write to this string. And then the formatted string, which is going to be assert, followed by the hex value of the program counter, then the program counter. And also, to make this function as isolated as possible, I'm also going to handle the initialization of the UART driver in this assert handler, in case the assert is called before UART init has been called. So first I'm just going to configure the transmit pin, so that the IO pin is connected to the transmit pin of the UART peripheral. And then I'm going to create a special UART init function for this assert handler. And I'm also going to move this to a separate function to make it more readable. I think I will also move the blinking to another function as well. And this assert handler is also going to have to take the program counter as an argument. And to retrieve the program counter, I'm going to use inline assembly to read the program counter register and move the value of that register to a local variable. So I will create a local variable here called PC. And then inline assembly, and I'm going to use the move instruction, move PC to, and I will have this inside if statement. So now after I've called this inline function, the value of this variable is going to contain the program counter, and then I can just pass this to this function here. And also modify. And then I can go on to implement the special UART functions. And I should never call this function under normal use. This should just be called by the assert handler. So that's why I'm adding this comment here. And just to reduce the complexity of the UART trace function when an assert is called, I'm not going to be using interrupts, and instead I'm just going to rely on polling. Because when an assert happens, I don't really care about performance, and it's just going to be simpler and less error prone to use polling instead. But in case UART init has been called before, in case we have called the normal UART init function and set up interrupts, the first thing I'm going to do here is disable the interrupt. And then I'm going to have a function that does the configuration. And I'm going to create a separate function for this. And simply move this here. And then as for the trace function, I'm going to loop over the string until the null termination. And use the function that I defined in the last video but then removed. So I'm just gonna bring that back here. So first I poll to make sure that the transmit buffer is empty. Then I fill the transmit buffer with the character I want to send. And if this character is a new line, I'm also going to send a line feed. Once again, this is the same function as I implemented in the last video, but then removed when I replaced it with the interrupt function instead. And if what I'm doing here seems confusing, you can go watch the previous video where I implement this UART driver. Okay, so now we can try to build all of this. Let's build the test assert function. Yeah, there shouldn't be a comma here. And then I'm also missing some includes. I need drivers, UART.h, as well as external printf. I need to include printf.h here since I'm using this function, the sn printf function. So now if I build, it still gives me an issue. So why is this not working now? Yeah, I forgot to save the header file. That's why it didn't work. So now if I flash and run this, I should be running the following function, the test assert function. And if my implementation works, I should expect to see this string and the value of the program counter. So let's flash this. Did not work. Okay, so I made at least 2 mistakes. This shouldn't be C here, and instead it should be line feed. And inside assert handler, I wrote this, which is also wrong. This should be this instead. So let's try to flash this again. And now if I reset. Okay, so now when assert triggers, it prints assert followed by the value of the program counter. But of course, by just looking at the program counter, it's not obvious which assert it was that triggered. So I'm also going to add a new makefile rule that I can call to get the file name and the file number from this program counter value. And there's a tool I'm going to use called address to line, which is part of my toolchain. So this function takes the final executable as well as the address as argument. Okay, so given this program counter value and this new make rule, I can simply call the following. So the same command as before, and then the address to line rule followed by the address variable. Yeah, so this gives me this value here. So test C colon 20. And if I go to this location, this is line 20, I can see that this is the assert that triggered. So doing it like this adds another step to find out where the assert happens, but at the same time it reduces the flash space my assert takes up and makes each assert take up the same amount of bytes. And while at it, I should also give some credit to the blog post where I found this technique, which is a blog post on the embedded blog called Interrupt Memfault. So this blog post, which talks about asserts on embedded systems, and I'm going to leave a link in the description to this blog post if you're interested. Okay, so with all of this in place, I can go ahead and format my code, run cppcheck, and then build everything, add my changes and commit. Or well, I'm also going to document this, I think. And then I can push it. And once again, make sure that it passes my CI system. And it did, so now I can go ahead and merge this pull request. This was everything I wanted to show in this video. And now I'm done with my trace implementation, and I'm not going to extend it any further. Of course, you can make this more sophisticated if you want to. For example, one way you could extend this implementation is by adding different log levels. So depending on the severity of the error, maybe you have a warning, a verbose log, or a fatal log, which is something you often see in many log implementations. But I'm not going to do that here because I want to keep my implementation more simple. Secondly, my implementation is just one way, meaning that I'm only sending data from my microcontroller to my host computer. You could extend this implementation to also send data the other way around, to maybe implement some sort of console interface to be able to send commands from the host computer to the microcontroller, which can also be useful during development. But once again, I'm trying to keep things a bit more simple here, so I will not be implementing that in this project. But this was all for today, so see you in the next video.